Hey guys, so today we're going to be looking at 2.2, the first day, and it's going to be looking at things a little more technical, and so hopefully you follow along and pay attention and ask questions. So 2.2 is about, it's more generic things about functions, more definitions really. The first couple are increasing and decreasing, what that means. The next are what relative minimums and relative maximums are. And the next, oh my goodness, we have a disaster. Oh my gosh. Oh my gosh, hang on. I can fix this. I can fix it. Just give me just a second. Just skip ahead or something. I'll fix it. Don't you worry. Hang on. We were about there. No, we got it, I think. Excellent. Okay, so sorry about that. Yeah, whatever. All right, so then we are looking at odd and even functions. So more definitions. So if you've forgotten how to do these, or you've forgotten, actually not really how, but if you've forgotten what these are and how to identify them, then by all means watch the lesson. And if you already know what increasing intervals are and relative maximums and minimums are and odd and even functions are and how to verify them, then go ahead and skip this. So increasing and decreasing. So there's definitions right below here, but I want to talk about on a graph how you can determine intervals of increasing and decreasing. And these are going to be intervals, which means that intervals are given from a specific x value to another specific x value. All right, these are intervals in general. And you write intervals out using interval notation, which has parentheses or brackets, and you read it from this number to this number, and it's basically like a list or like a set of x values here that all are doing a specific thing. That's an interval. So, and I'll explain the parentheses and the brackets here in just a little bit. But an increasing function is a function that as your y values get bigger, as your x values get bigger, your y values are also getting bigger. Okay, that is an increasing function. So as your x values get bigger, your y values get bigger. And what that means is you start by looking somewhere. Imagine the farthest to the left the graph goes, or actually where the leftmost part on the graph is, and then you start moving to the right, because that's the x values that are getting bigger, right? The more you go right, the larger your x values. So you start looking at a point. So say I was looking from this point, and I start looking at my graph. As I look to the right, if my y values are consistently and only going up, then that means that you have stumbled upon an interval of increasing. An increasing interval. And if you look here, when you follow the graph with your eyes to the right, it's going up. It's still going up. It leveled off a little bit, but it's still traveling up. Still traveling up, still traveling up. Now, here, it looks like it has stopped traveling up. And I'm going to go ahead and pretend that it did stop traveling up. So, for the sake of showing you how to write an interval. So, the first interval of increasing would be from this x value to this x value, okay? That would be an interval of increasing. So it's increasing in that interval. And that is from negative 1, 2, 3, 4, 5, 6, 7. We'll call this 7.7 just for the sake of discussion. Negative 7.7 to, we'll call this negative 1 to negative 2.6. All right, so from negative 7.7 to negative 2.6, you have an interval of increasing. As your x values are going up, your y values are going up. And I don't mean up as in, like geographically. I mean as they get bigger, okay? As they're going up as in, you're getting higher and higher numerically. So then it flattens out here. So we are not increasing or decreasing here. It's just flat. But before that, I want to talk about whether you use parentheses or brackets. Now, in intervals of increasing and decreasing, you need to look at, actually, I don't even know how much specifics I wanted to get into this in Algebra 3, or your college algebra class. So if you are continuing on in math, you're going to need to be pretty specific about what's going on here. But for me, I'm not that picky, right? So I would say for you guys that since it starts here and it continues to climb and it starts climbing from here, you include this point. And the way you include points is by using brackets. So this is including. And you would include this point too, because that's the last point that it has been increasing on, okay? So then it flattens out, and then it continues as you go to the right again, as your x's get bigger. Notice your y's get bigger, your y's get bigger, your y's get bigger. You're still climbing. So it continues to climb, looks like forever, okay? So from this point here, onward to the right, this is another interval of increasing. Wow, I combined my E and my A to form a new letter. So it's still increasing because it's an increasing function. As your x's get bigger, your y's get bigger. All right. So this interval would be from this x value to infinity. So we'll say this is negative 1.2. Negative 1.2 to infinity. Now we'll say we'll include negative 1.2 because it's the start of where it increases. And then infinity is never included. Positive and negative infinity is never included. So this means it is excluded. Okay? Now, let's look at a decreasing graph. This is one that is going up and to the left forever. So if it had been going left and up forever, you have to imagine the very farthest to the left that the graph can possibly have existed, which means you have to imagine at negative infinity what this graph is doing and what it looks like. So if it's going upward in that direction, up in this way, right? If it's going that way, then if you imagine, stretch your mind out to where it's at negative infinity, like say this is negative infinity, right? Say this is the cutoff for negative infinity. The graph would be really high up. So that's the value you want to start at. And then as you continue to the right, that means as the x values are getting bigger, right? As you go right, the x values are getting bigger. What is happening to the graph as you're going to the right? Try to imagine. The graph was way up here, and it stopped at infinity, right? Then, as you went to the right, the graph continues to come down, right? It continues to come down, and it meets right here. So that means as your x values get bigger, these y values are going down, 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 down. They have to if they're going to connect to this point. So that means starting at negative infinity for the x value, your graph is already decreasing. It's going down, 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 down until it meets up here. So here is an interval of decreasing. And it's decreasing starting at negative infinity. And remember, we never include infinities. And it continues to go down. And you have to figure out, is it ever going to stop going down? Or is it ever going to level off? And the answer is no. It looks like it continues to go down forever. So it is decreasing on the entire interval of the graph's existence. From the moment it starts to the moment it ends, it's a downward slope. And so that means that's the interval of decreasing. So here's your definitions for any of you who want to write them down. F of x, an increasing function, is where if f of x is increasing as your x value is increasing. And f of x is like y. So if y is increasing as your x value is increasing, then it's increasing. Then if y, or f of x, is decreasing as your x value is increasing, that means as you're going to the right, the graph is going down, right? As you look to the right, the graph goes down. Okay. Now, let's look at this example. Within the interval from -10 to a +10, state all intervals of increasing and decreasing. So I will do the first one with you, and we'll see if you can get the second one. So, this is a bad example, actually. No, we'll be good. We're fine. I'm mistaken. Or I was confused for just a second. We're fine, though. So, this parabola, we don't know where it's going to cross at -10, because remember, we're interested within the interval. This is the interval we're interested in, from -10 to +10. What's happening to the graph? We don't exactly know where the graph is going to be whenever it gets to this point. We know it's going to continue to go up like this, but we don't know the specific y value that it's at. That's not relevant, though. What we do know is, based on the shape of the graph, that if you were to zoom out and examine the graph from this point here, as soon as you go to the right, as soon as your x values start to climb up, your y values are dropping, really. Now we're at 7, and we're at 5, and we're at 4. No, we're at 8, and then 6, and then 4, and then 2, and then 0. The y values are still decreasing, going down and down and down. These y values are continuing to go down as you look farther and farther to the right. As your x values are getting farther, or bigger and bigger and bigger, the y values are going down, 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 right? It's basically got to do with slope, guys. If the slope is negative at that spot, then it's decreasing. If the slope is positive, then it's increasing, right? That's a more simple way to look at it. So, an even more simple way to do it, if you could slide down from left, or if you could move to the right on the graph and slide down, then it is decreasing, right? So you could be up here on like some sort of sled and slide down as you move to the right. And then right here, you're going to stop sliding down. Well, I mean, you're still going to have momentum in a slide, but, whatever. We're not considering that. At this point, you start climbing up. This is where you are increasing, okay? So from here, as soon as we are as from -10 all the way until this point here, which is 2, the x value of 2, you are decreasing. So we're going to erase some of this crap that's on our screen here. So decreasing. So I'll write a D for decreasing. From -10 to 2. Now, here's the catch. You don't want to include 2 in the decreasing interval, because at 2, you are transitioning from going downward to going upward, which means you are level. And that means you are not going down anymore, all right? So that means you can't include 2. So we use a parenthesis. And that's okay to have one bracket and one parenthesis. Then, immediately after 2, from this x value, immediately afterwards, going right, you start to climb up. It's like climbing up a mountain. And so that means we're increasing all the way up until you hit the end of our interval, which is from 2 to 10. So you're increasing from 2 to 10. And you do include 10 because it's specified that you include 10. And if you were to look at 10, the x value, you would still be climbing up, right? You didn't level out any because the graph continues to go up. But at 2, remember, you were level. So that means you're not going up, which means you don't include 2. All right, hopefully you have, I know it might seem a little confusing, and that's okay. Just hopefully try to think of it as basic as you need, or as complicated as you'd like. I think the simplest way to think about it is if you're looking with your eyes going from the left to the right, if you're going downward on the graph, you're decreasing. If you're going upward on the graph, you're increasing. So starting here, You tell me the intervals of increasing and decreasing, all the way from -10 until +10. Tell me all the increasing and decreasing intervals. Okay, so starting here, as you move to the right, you're going up a slope. That means you're increasing. So this interval is an increasing interval. So you're increasing from -10 all the way to -2, this x value. Remember, we're looking at x values. So from -10 to -2. Actually, I need more space. I'm going to scroll down just a bit. Okay, increasing from -10 to -2. You don't include -2 because you level off, right? That's the top of the mountain. You can no longer say you're climbing the mountain if you're at the top of the mountain. Then, after that, you start decreasing, going down a hill. This is the interval, the next interval, and it's a decreasing interval. So you're going to be decreasing from -2. You're going to slide down, keep going down the mountain, however you want to think about it, until 5. So from -2 to 5. And you don't include these points either because that's at the top, so that means you're not going down yet. And this is at the bottom, which means you're no longer going down. Okay? And then immediately after 5, you start climbing back up. So then from 5 to 10, including 10, because actually, this is a mistake here. Good thing I see that. Sorry about this. The interval states to include -10, so we need to include it in our interval. Hello. Okay. So, at -5 or at +5, you cannot include that in the increasing interval because you're at the bottom of the hill, right? You can't say that you're climbing the hill at 5, but right as soon as you start moving again, you're including it, or you're not including. You're moving uphill. Now we have these two intervals. We need to combine them into a single interval, and to do that, you put a U. Simple as that. That's a sign for a union. It combines two intervals into a single greater interval. All right, and that's the end, because we got to the end of the interval that we're interested in. Now, relative minimums and maximums. These are easier than increasing and increasing. Basically, when a function changes from increasing to decreasing, or from decreasing to increasing, there are relative minimums or maximums. And that should make sense. When you change from going uphill to going downhill, well, that's right here. Change from going uphill to downhill. This is a relative maximum because it's the highest point. It's like a peak, right? It's the highest point. So this is a relative maximum. And then a relative minimum is where you're changing from decreasing to increasing, where you're going down, 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 and then going back up. It's the valley. It's the very bottom of a hill. Okay, this is a relative minimum. And the reason they're called relative is because they're only considering the points around them. They're not considering the graph as a whole. Those are called absolute maximums and absolute minimums. So at peaks and valleys, those are where you have relative minimums and relative maximums, or the other way around, based on the way I said it. And this is a relative minimum, a low point on the graph. This also happens to be an absolute minimum because the graph never gets lower than at this point here. When you're stating minimums and maximums, you state the y value. In some texts, they also tell you to state the x value, but typically it's the y value that's the relevant point for absolutes. For relatives, though, since they change, you probably want to include the x value as well. So here you'd say there's a relative maximum at -2.7, a relative minimum at 5.3. And here you could say there's an absolute minimum at 2.5, or just, wait, this is -5. What? How did I notice? If you notice this, good on you, I guess. So, anyway, That's relative minimums and maximums. Man, we are... Ew, gross. This is going to take another 5 or 10 minutes. I apologize for the 30-minute lesson. Find the local minimum and maximum of the following function by graphing them or calculating the min and max. So if you got a calculator, let's go ahead and pull that out, and I'll show you how to do this. So here's our calculator. If you know how to graph the function by hand, that's fantastic. I know how to graph this by hand. It is an absolute value function, which means it looks like a V. It has moved right 2, down 1, and is vertically stretched by 2. So it's moved right 2, down 1, and it's vertically stretched. So I know that's what it looks like. But if you don't, then you can hit y equals on your function on your calculator and put this in it. So 2, and then to put absolute value, you go into math, and then you go to number, and it's the very first one, ABS. Absolute value of x minus 2, so x minus 2, close parenthesis, minus 1, and graph. Look at that, exactly what I predicted. So the relative minimum is also the absolute minimum, and it is this point here. That is where you stopped going down, and now you're going back up. So this point here is the relative minimum. And it is at 2, -1, or -1. For relatives, I recommend this. For absolutes, that's okay. Or if they specify what is the minimum value, then this is good. Anyway, I'm not too nitpicky in Algebra 3. I just recommend you use ordered pairs. Why not? Okay, even and odd functions. You should write down even functions symmetric about y-axis, odd functions symmetric about the origin, which means reflected over x and y. So it's even functions are reflected over the y-axis and symmetric about the y-axis. Odd functions are symmetric about the origin. You should have that memorized. And you should probably not write this down. This is just for to demonstrate. So famous even and odd functions. So the sine function is a famous odd function, because if you were to reflect sine over the y-axis, here's the y-axis, a reflection would mean that this value flips over here, this value flips over here, this value flips over here, this value flips over here. That if this was a reflection of the y-axis, then the graph would show up here. It would lay on top of itself. But it does not. It's not here. It's down here, right? So this is not an even function. However, if you were to try to reflect this over the origin, which means flip it over x and y, so here's how you do that. First, let's reflect it over one of the axes. It doesn't matter. Let's do the y-axis. So if you were to reflect this over the y-axis, every one of these points would start to flip. And what that would look like is this. That's what this would look like. All of these points, this one flipped here, this one flipped over here, this one here flipped all from -9 all the way to, it should have flipped here, right? And this one flipped over here, right? They reflect over the y-axis. And now you're saying, okay, well, it's still not on my graph. It doesn't look like my graph, but over the origin means over x and y. So we reflected over y, and now we need to reflect over x. And so if you were to reflect over this axis here, imagine that you folded your paper in half where the graph would lay. That's a reflection. So if you look here, you're at -4. Well, that reflects up to +4. This reflects, this reflects, this reflects, this reflects. And they reflect like a DNA strand. And if you notice, they would lay right on top of each other. And this is a lot easier to do on like paper that you can fold it and see. Like if you had your piece of paper, you could take the bottom edge of it and fold it at this crease, and you would see that it touches exactly where this is. So that means it's symmetric about the origin, because if you reflect over x and then y, you have the same exact graph that you started with. That's what's important. If you do the reflection and you have the same graph that you started with, that means it's symmetric about that axis. Now this function, cosine of x, is an even function because if you were to reflect it over the y-axis, it would lay directly on top of itself. If you were to fold this edge over and have a crease here, where this is at the, this edge flips over here and there's your crease, it would give you one curve, and it would be this curve here, because this piece would lay on top of this piece, this piece would lay on top of this piece, this piece would lay on top of this piece, and so on. So I just wanted to show you this symmetry and how that relates to even and odd functions. So moving on, here's what we'll be dealing with really in terms of how to actually verify if something is even and odd. So in the first lesson, we were talking about evaluating functions at given values, and we did this once. We did f of negative x. We're going to do that again. If you plug in negative x into x, and you get the same function you started with, the function is even. If you plug in negative x, and you get like a sign flipped version, a negative version of your function, then it is odd. And if neither of those things happen, then it is neither. So let's do it and find out. So we're going to try to do f of negative x. That's what we're going to do in both of them, okay? So just evaluate this, and you should be good with this. Just substitute in negative x everywhere you see x. So you get negative x instead of x cubed minus 6 times negative x. And then simplify. So negative x times negative x times negative x is a negative x cubed, because a negative times itself 3 times is still negative. And then here this becomes positive 6, because negative times a negative is positive, and 6 times x is 6x. So now we have to compare to the original function. Is it exactly like the original function? Is f of negative x equal to f of x? Because this is f of x. And no, it's not, because if you look, the x cubed is supposed to be positive, but ours is negative. And the 6x is supposed to be negative, but ours is positive. That comes into play right here. If we were to factor out, now this might be confusing, so just try to bear with me. If you were to factor out the negative sign, you would get negative outside, and then you get a positive x cubed minus 6x. And this is correct, because if you were to distribute it back in, you would get a negative x cubed and a positive 6x, okay? So if you look, this is f of x cubed minus 6x. Well, look at that. X cubed minus 6x, but there's a negative sign out front. So this is correct. This is what this is. It is a negative times f of x, a negative times f of x. That means the function is odd. And a simpler way to think about this is if all of the signs have been flipped after you were evaluating f of negative x, then it is an odd function. If everything is exactly the same, then it is an even function. Okay? You might be asking, why do we care about even and odd functions? Well, this is for, like, college algebra is supposed to be an intro into calculus, and in calculus you have a lot of interesting tidbits of even and odd functions based on their behaviors. So it's basically like a foundation for moving on into calculus. Anyway, so here we're going to see if this function is even or odd. So what you have to do is you evaluate it at f of negative x. And you plug in negative x here, and you simplify. And what you end up with is a negative times itself 4 times is a positive. So you get positive x to the 4th minus 2, and then again, negative 2x times, or negative x times negative x is a positive x squared. And notice, this is exactly the same. X to the 4th minus 2x squared, x to the 4th minus 2x squared. This is an even function. And this one up here I didn't specify, but this is odd. Now this one here is the last one we're doing, and this is wrapping it up. So here, let's look at h of negative x, because this is called h, not f. And that is negative x squared, quantity squared, plus 2 times negative x plus 1. Well, this is x squared minus 2x plus 1. Now compare. Is it exactly, are these two things exactly the same? No, they look very similar, but this is a positive 2x and this is a negative 2x. So it is not even. So then, are all of the signs flipped? This is positive, 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 so a odd function would be negative, negative, negative. Well, this is not negative, negative, negative. There's only a single one of them being negative. So this is neither odd nor even. So this is neither. All right, here's your homework. If you have any questions, let me know. All right. Sometimes these lessons are just going to run long. If you understand things quickly, then feel free to skip ahead. All right, take the lessons at your own pace. I give you enough time to watch all of these in class and have most of the time to work on homework too. Anyway, please, for my sake and your own, don't be a lazy bum. Do your homework and ask me questions, and I'll catch you next time.